This is going to be a lesson on sketching the trigonometric graphs. In a previous lesson, we already learned how to sketch the basic trigonometric graphs. So let me just start with a graph of the cosine of theta. Now we would like to investigate the effect of swapping this really simple function for a version that's undergone what we call a linear transform. Now in this expression, a, omega, phi, and h all have to be particular constants that we can choose to be anything we like. Under a transformation like this, the shape of the graph doesn't change at all. The only things that can happen are that the graph gets squished in the x direction, y direction, or that it moves around to somewhere else. Now we already said that these transformations aren't actually applied directly to the graph, but to the axis instead. Now in order to actually help us visualize the axis moving around, I'm going to draw a little marker that's one unit in both the theta and x direction. Now since transformations are applied directly to the axis, I'm going to imagine that this axis was moved to the right by some amount, moved down by some amount, then stretched in theta and squished in the x direction. As you can see, all four of these things happened. The axis moved to the right, then it moved down, it got longer in the theta direction, and it got thinner in the x direction. Now in this case, we'd actually like to draw the graph from the perspective of this axis. And if we do that, we get something that looks a little bit like this. Now as we said, if the axis undergoes these four transformations, then the graph is going to undergo the opposite transformations in the opposite order. Now we've also drawn this from the green axis perspective, so it might be nice to watch the red axis morph into the green axis again on this new graph. Now because the trigonometric graphs keep repeating the same shape over and over again, we can just copy and paste this little shape over and over to make the whole graph. Now in order to actually graph the function on the right, we're going to need to use a little bit of a trick. We're going to track a little box on the input function that we can choose to be whatever we like. And then we're going to see where it goes to under the action of this transformation. To do this, we're just going to need to track where the corners of this box move to. So actually drawing the graph on the right is a two-step process. The first step is to work out what transformation you applied, and the second step is to actually go ahead and map the points through that transformation. It would be a good idea to investigate a specific case, so let's bring on a piece of paper and write one out to actually see how this would work. Now in this question we're asked to graph the height of the water at a particular beach in some particular city. Somebody has already measured the tides and told us that it obeys this function over here. And all we need to do is actually sketch x versus t directly. We can see that it's modeled by cosine, so we want to find the transformation that takes x equals cosine of theta to this function over here. To do this, we're going to draw a graph of the cosine of theta and track 2 points around as it moves. In the first step, we're going to want to figure out the transformation. So to do this, we're going to want to write it in the form x equals cosine of theta. So first we're going to move the 5 and 2 to the left-hand side. We start by subtracting 5 from both sides to move the 5 to the left. And then we go ahead and divide both sides by 2 to get the 2 on the left. Now if we look carefully, this capital X is going to be the exact same thing as this, and this theta must be the exact same thing as this. So the only thing we need to keep is the transformation, so let's get rid of everything else. Now since we actually want to graph the x and t axis, we should make x and t the subjects of both of these equations. So I'll go ahead and do that on the left first. We started by multiplying the 2 to both sides, and then we should just add 5 to both sides to get the final result. Now this is the only part that we need to keep, so we'll get rid of the working out again. Now we're just going to go ahead and do the exact same thing for the right hand side. So first we're going to start by adding pi on 6 to both sides. Then we're going to multiply both sides by 2 on pi. When we do this, we see that lots of things cross out, which leaves us with our final result. Now again, we don't need any of this working out either, so I'm going to get rid of it too. Now that we know what transforms we've used, we should go ahead and map our 2 points directly through them to find their new values on the new graph. Now the first point is theta equals 0, capital X equals minus 1. So we can map it through these two transformations to find out exactly where it maps to. To do this, I'll bring out the calculator. Not that you really need it, but I'll just type it anyway. Now when theta equals 0, we can use this equation to figure out exactly what little t should be. So let's use the calculator to figure that out. It's obvious enough, but since we subbed in 0 here, we just get 1 on 3. Now, when capital X equals minus 1, we can use this equation to figure out what little x is going to be. So from this, we see that the point 0 minus 1 just gets mapped to 1/3, 3. Now we're going to try the second point, 2 pi 1. Again, we'll start by putting 2 pi in for the value of theta to find t. Now as you can see, this just gave us 13 on 3. Now if we go ahead and take this value 1 and sub it through this equation, it'll give us the value of little x as well. Now if we just get rid of the calculator, this gives us all the information we need in order to draw the graph. Now we can just sketch the graph in this region and repeat it over and over if we need to. Now I want you to note that the bottom left corner mapped to the bottom left corner, and the top right corner mapped to the top right corner. This doesn't always happen, and when it doesn't, you actually have to flip the graph to put it in the right orientation. Now with our example complete, let's say a little bit more about the original graphs. Now I'm going to leave this as an exercise to you, but you can always rewrite this in the following form. This means that this is just capital X and this is just theta. I'll also get you to check that we can write the transformation in the following way. Now under the action of these two transformations, the box can be mapped to these two coordinates. Now if you go ahead and look carefully at the graph, we can go ahead and tell you what these three numbers actually do to the shape of the graph. First off, this h just shifts the graph up by h, so it tells us the new baseline of our graph. Now since we just stretch capital X by a, then this a just tells us how tall our graph is going to be after the transformation. Now to avoid too much clutter, I'm going to remove this because we don't really need it anymore. Now if we went ahead and put theta equals 0 through this transformation, we'll notice that it's just going to map to minus phi on omega. So in a sense, this phase over here is related to the starting point of the graph. Now since the angular velocity of omega just divides the graph, it controls the width of the graph. Now I'm not saying that the distance from here to here is exactly equal to omega, but what I am saying is that making omega bigger makes this width smaller. Now this actually leads us to an interesting question. If omega doesn't directly control the width, how can we set the width to be any number we like? I'll go through this with you in a blank page. So far we've been tracking the cosine of t with a box that goes from 0 to 2 pi. Now we know that if we swap the t for a 2 pi t, we know this is going to end up squishing the box by a factor of 2 pi, so the new box will be between 0 to 1. Now I'm going to go ahead and swap 2 pi t for a 2 pi t on capital T. This will let me stretch out the box to any size capital T that I like. Now if we think about this for a moment, we'll notice that this thing in front of the t was called omega before. So that means omega is the same thing as 2 pi on this capital T, which we call the period. Now just by looking at these two, we can see that omega is just the same thing as 2 pi on T. And with this, we've completed our discussion on how to sketch trigonometric graphs.